If the red team were in prison. Okay.
Well, a good red team, or a good one not.
If the bad red team is in prison.
Where is that? So, wait, what is
The good ones work for the government login.
I know red team and blue team, but
Well, not really.
Is a defensive person. And a black
Okay,
hat
guys,
is an
attendance
offensive
starts here.
so it is like
Yeah, but this one has a lot of political content.
We can say legally.
It is.
Are you victim secrets or not?
Okay, so like, you know the difference between like a freedom fighter and a terrorist?
but yes, I do.
It's not an objective distinction.
Right.
It's a political
No.
distinction. That's the difference between white hat. So that's white hat.
Okay, gotcha.
Political distinction.
No, don't call me Chloe. Come on. No, come on.
No, I'll just wait until you're in the cube and then you're
Yeah,
like,
no, wait till I get put in the cube and then.
We're gonna see just like a glowing outline into the cube, and it's just gonna be you glowing.
It's gonna be me.
What's up, Alan?
Major respect to Halen.
Where is this? Okay, so if you got the VM up in insecure programming, there's a bunch of in the source insecure programming directory, there's a bunch of programs.
I should
The one we're going to look at first is ABO1. It should also be on the canvas if I published it. I apologize profusely to everybody for my inability to perform a very basic administrative task. I am a new professor.
What?
Okay, so we're going to take attendance real quick. You're going to write down your last name and if you're, or your full name and email address, and if you're a white hat or black hat. This is just a base survey. How do you consider yourself? What do you want to do with your life, black hat or white hat? And then we'll talk about what the difference is materially between what you have to do as those people.
Jeremy.
Jeremy? Let's go. We'll find this
Following
pretty direct. I'm sorry if it's boring, but maybe the second example will be interesting.
Oh, I need food ready.
Oh yeah, go for it.
And if anybody still needs like a VM to do the assignments, I sent a form in the Discord, fill it out, it takes 15 seconds and you have a VM up.
Yeah, if you don't have the VM up or you don't have a way to get to this stuff, find a partner that does, please. Please raise your hand if you don't have access to a VM right now. I hope that means everybody has one, or they're not paying attention enough to care if they have one or not.
I just have like a random question. I'm like, I booted up the VM, but like, how do I like log in?
Oh, yeah, okay, so
I have like no clue.
yeah. The user is Dean,
Yeah.
and the password is Moriarty.
Oh, okay.
Where's
Awesome.
the,
Write that down.
You will have to Google that every time. Make sure you're spelling it right.
I did not spell it right.
It's like the Sherlock Holmes thing.
Yes,
Yeah.
Moriarty. But it's not from Sherlock Holmes, it's from something else.
Oh, what is it from?
Wizards of
Okay, yes, okay, so you got,
Yeah.
all right, here we go.
It's like working.
Are you
and then there's ABO1.
Is that actually you got it all?
And then there's also in there, should be, a program. So you have been provided with an exploitable program. It's the same program we looked at in the second class. When we learned about assembly, we walked through this program.
I got a VM running.
I should really mirror this screen.
And like, I think she knows so much more than I do. I feel so bad.
It's okay. I think
We could.
Oh, that's fair.
I want to think about
Alright, this is much better.
What's happening now? Very? No, it's very.
So while you guys are getting set up and finding this stuff, I want to talk about a small syllabus change.
Oh,
I've removed a lot of work from the syllabus and made it a lot more simple. So there's going to be the 5 or 6 homeworks that are going to be worth the majority of the grade. There will be one midterm. There is a midterm class day listed. That's basically going to be an extra office hours. I'm going to give you that midterm early as a take home. And the midterm office hours are immediately before spring break. And I will pick up, you can either pass it in then or you can pass it in after you get back from spring break if people need extra time. There are people who need extra time who have accommodations. I hope that giving you that span as a take home would suffice for that. If people need extra time, just let me know.
Is the midterm a programming assignment?
It will be just a set of like 4 or 5 questions. There'll be essay questions, and probably one of those will be like, here's a program, draw the stat.
Is there a final too? Because I saw in the syllabus that it had like a take-home final as well.
What we're going to do for that is actually there will be a final project that you all will pick up, and then the last 2 classes are presentations on that final project. There will be no final.
Oh,
Cool. So I've cut a lot of work out of this, and the reason I did that is because people here are at extremely different levels. Some people have come in, they've already done a lot of the example programs, and some people are brand new at this, and I need to figure out a way to be able to curve it all so that it's reasonable for everybody, right? From all these different places. I want all of you to get an A on this class, right? And I'm going to do my best to make that happen. And so even when I do the curve, there will be a set of people who solved everything. I'm going to take them out of the curve entirely. And then I'm just going to curve the rest of the people. So everyone who's got an A, you don't have to fight against them. Don't worry about it. Right? So it's going to redound to your benefit.
what should we do with that?
We're going to be doing, in the VM, you've got a program directory that's insecure programming, capital I insecure programming. Is it, what's the full path of that, Jade?
On the VM?
Yeah. Is it source insecure programming, insecure
I
programming?
think it's in the root, isn't it? Isn't there an
It's in
insecure
the
programming
home
dash
In the home root.
Yeah.
Okay.
It's in labs.
My lab's here.
There's actually 2 copies.
Well, yeah,
Yeah, there's like 2 copies of it.
It's like your programming master, and then you have another one in labs, which I think you move some files out.
Yeah, the lab one has the make file, the other one I don't think has the make file.
Yeah,
Okay, so it
it's
is
all the build binaries.
So then what should we
logistics
do?
problems. In the labs directory, there's insecure programming. It should look, hold on, I'll show it to you over here. It should look basically like this. It should have the gadgets.asm in there and the make file. If you look at the make file, should link that gadgets in there, and we'll see why that's in there in a second. But the program is already compiled for you. That make file compiles a simple version of the binary. I pulled out all of the optimizations on the compiler. We will add those optimizations back in for you to see what the difference is later, but for now we're working on the simple case.
I don't think gadgets is in it.
Yeah,
At least I don't see it.
folders, I see gadgets, or the Python of programming.
All right, and I will add
I
those.
don't get it.
If you've got access to the canvas, the stuff that I'm looking at is directly in there. You could just pull it down off the canvas.
Yeah, gadgets isn't in the VM at all.
Okay, cool. So yeah, just pull it off the canvas, grab it from a friend. Holy
Will
squeaks.
be used in.
Yeah. We need to find a room.
We can open it in VS Code and then drag and drop.
I do.
We can make it. I've never.
Yeah, so, okay, hopefully this is published. Federal materials. Lab 1, February 11, Lab 1, that's everything. The best place to grab it is from Canvas.
I don't think it's published. Yeah, I don't
It's
think
there. What?
It's under-
It's right there.
It is there. Just
Do like
Now it's published.
It's published.
All right,
Oh,
here's the final version. It's got the binary, it's got gadgets.asm, it's got a compiled version of gadgets, it's got the make file, and then it's got the second program we'll look at later. It's got the template for the exploit you're going to use, and it's got a GDB cheat sheet. So pull it all from there. That means everyone's going to be working on the same project.
Right, but that doesn't have the lab.c. It's a different thing.
Oh.
Yeah.
So yeah, it's still not published.
Yeah, it isn't?
No. Unless we like gadgets.asm and
Is there a way you
everything.
can zip all the files?
Could we do it in Marco like that?
Yeah.
Yeah, February 4th contains.
Yeah, we have introduced that to Stack.
February 4 has the same program with all this stuff in it, but it's not, it's an older version. It's the one we looked at on February 4th. The one in February 11 will put you all on the same thing.
Oh,
You
there
guys
we go, I see
wanna
it
do
now.
on a zip file with all this in one spot?
Yeah.
What I'm actually gonna do is just tar up all of this.
It's just resume covers it, right? That's it.
I never remember.
Everybody feels.
Wait, so how could you with these?
Oh, you're not right, you might just
Yeah, I teach you. They don't care.
yeah. Do you think you're?
All right, so
No, I don't think you will.
the whole insecure programming directory is now in that module as ip.tgz. That's going to be missing lab Y. Don't worry about lab Y for right now. We'll get to that in a little bit. That'll be an easier single download.
Or I guess log in the queue is in the VM.
So what we're going to cover today is how to use your debugger. And then we're going to cover how to use Python to interface with programs in the way that I'm going to want you to do so for the homework. Okay? So this will be very hands-on for the homework. This is a simple example. This is, in fact, the very simplest example that I can possibly show you. And I don't want you to be disappointed with that, because we're going to do some much harder examples afterwards. So if this is double coverage for some of you, don't worry about it. When you do the second example in the homework, you will not have seen that before. Okay? There are reasons that I am giving you these very simple cases firsthand, and it is because everything becomes complicated by simply aggregating many simple pieces together, right? It's the same thing with assembly. Assembly instructions, very simple. You put a billion of them together. Now it's really complicated for you to understand, right? We start with the simple case to minimize the frustrations. So we're 32-bit, not because I don't want you to understand modern systems, but because you're going to type in addresses all the time. And it's very much easier if you're hopping between windows to remember 8 numbers in chunks of 4 than it is for you to remember 16 of them, right? I've double taxed your memory if you're writing 64-bit addresses all the time, right? We turned off ASLR not because I don't want to teach you how to bypass ASLR, but because before you can do that, you need to start being able to recognize in hex where addresses are coming from and what data structures look like reading a hex editor. And if I ask you to do that in 64-bit, it's going to be twice as hard for you to get a handle on it. Now you've got 2 or 3 compounded problems to try to deal with. So we're start with the small problems and we'll build up, okay? Other things people ask very often is, when are we going to do heap stuff? I already know how to do stack stuff. Here's the difference between a black hat and a white hat. This is the fundamental difference. If you are a white hat, you do one heap example, and you have control of EIP, and now you're done working. That's it. You can go and get your CVE, and you can tell the engineering team to go fix that bug, and you can go do something else. If you are a black hat and you get EIP, that's the start of your 6-month journey. Because once you've got EIP, you need to make the sucker work, and it needs to be reliable. Okay? When we test your example codes with the auto grader, we are going to mess with the environment. That means if you were sloppy, it won't work. And I will teach you what it means to be sloppy and what it means not to be sloppy today, looking at this. And that's why the gadgets is in there. You don't actually need it to get this done, but you need it to get it done well. Okay? Right, the buy-in cost for me as a black hat to actually working on a bug is somebody handed me something as an exploit dev. They already have EIP. That's when I know it's worth working on, right? If you're a bug hunter, that's going to go all the way. That's something different. Once you get EIP, you're going to have 5,000 crashes. And 3 of those are going to get you EIP. And then those are the 3 you're going to work on, and you're going to throw out all the rest of them. Even if they might be usable, those 3 are the ones that are worth wasting time on, right? So in this example, we've talked about this already. We've gone through the assembly. Is everybody feeling fairly confident in their ability to read through that assembly, understand the flow of that program? Yes, good. What's the bug? Anybody? The stack overflow, what does that mean?
That means that we're taking in a buffer that we don't measure the size of.
Correct.
Meaning that we can go beyond the unstacked by the buffer.
Yep.
And then we can overwrite to
Okay. So what allows us to write past the end of that 256? There's a quality about a string that strcpy is looking for to know when to stop.
Looks for a null byte.
Looks for a null byte, right? So we're going to send it a string that doesn't have a null byte within 256. It's going to be longer than that. We've looked at what the stack looks like when we call strcpy, right? In this class today, your first step before you do anything else, even while I'm talking if you like, is draw the stack for this thing. Okay, and draw the stack when you get to strcpy. So. You're going to be drawn.
Is that like
Man, I totally didn't turn on the video, the voice recorder, so I hope.
yeah, it's just
I don't know how to test that. I'll see if
you need to open it.
I actually don't know how to test that. Let me see if I can figure that out.
Test if echo is going.
Yeah.
If you just like go to the Echo 360 thing, it'll say it's recording, but you can't like check it while it's recording.
All right, I'll turn on the voice recording right now then. Leon is not here to do timestamp, so that's okay. We haven't really, I'm going to have somebody timestamp the audio that I'm going to start now. I haven't even gotten to the topics yet, so it's fine.
Okay.
Are you taking timing, Jade, or shall I have August?
I'm sort of doing that. I'm also doing a bunch of things.
Yeah, okay. August, can you do timing for us? Ready, go? Let me know when you're ready to start.
What should I timestamp? Are you gonna say it?
The notes are in the Discord. I have dropped the notes for the class.
Oh, okay, I see it.
Yeah, it'll look like that. GDB usage, disassembly, running and restarting programs, breakpoints, et cetera, et cetera.
Okay, let me get my stopwatch.
Yeah, just do timestamps relative to 1 o'clock. Echo 360 is working and should be working relative to that.
Okay, cool. All right, so then when you're ready, I'll press this button and it'll be 3:19 that the timing starts up.
Okay, I'm ready.
Ready, and go. So starting at 3:18, that means we're 18 minutes plus our 360 time, and I'll have to correct for that later, but that should be okay. I don't have my microphone on either, which is because it is missing. Here it is.
Yeah, it appears to be live.
Okay.
Check. Oh yeah.
All right, so the goals of class today are to get you familiar with using debugger and make the debugger your number one best friend in the entire world. When you have a question that needs answering about a computer program, you ask your very best friend in the whole wide world, and its name is
Debugger.
Debugger. Its name is the debugger. You ask the debugger. If I catch you writing print statements in your code to figure out what's going on, that will be the only thing that fails you in the class. Everyone else gets an A. So try to trick your friends into using print statements to solve their problems. You get everybody else in the class an A. That's how a hacker would think about it. So the major problem with using the debugger is that it's extremely opaque if you don't know what you're doing, right? Anytime you ask it a question, it gives you a set of hex numbers. And if you don't know how to orient yourself on those hex numbers, it doesn't make a whole lot of sense to you. And so the first thing that you need to do when using the debugger is the same thing you need to do when you are starting to think about reverse engineering, which is don't just go messing around. Come in with a set of questions and come in with kind of an idea about how you want to answer those questions. And what I mean is this. You are going to look at this program and figure out what it does by reading it, basically, and drawing your stack. That's number one. Okay? So we've identified our bug, we've drawn this stack, and then the question is, how do I know that my stack that I've drawn is right? And the answer is, we are going to run the debugger to the point at which we drew the stack, and then we're going to look at the memory and validate it. And everything we think has happened when we drew our stack, we should be able to see that in the debugger, okay? So you will have an assumption, you will explicitly list what the assumption is, and then you will validate it in your debugger. And you will stepwise walk through all of your programs like that, okay? And what this allows you to do is validate all of your axioms are true, and you are using a combined strategy to do this. You are using static analysis and dynamic analysis in lockstep together. There are two ways to understand what a program is doing. Static analysis means I'm looking at the code in a disassembler. I'm looking at the code on a piece of paper. I'm looking at the assembly, and I'm reading it, and I'm deciding what it does. That's static analysis. Dynamic analysis is I'm running the program, I'm causing it to stop at certain points, and I'm looking at what it's doing. Or I am stepping single step through the program and watching it do it, right? So that's the difference between Marcus Aurelius deciding that vultures are fertilized by the wind because he's never seen vultures get it on, and Marcus Aurelius following vultures around all the time and watching them get it on and figuring out that they don't make baby vultures unless that second part happens, right? I'm guessing based on what I can see, or I'm actually doing the testing to figure it out. And we do it together. We create assumptions by coming up with hypotheses, just like in physics, and then we run tests to validate our hypotheses, right? And so those are the steps that you're doing here. Now, the way that we break down the problem to decide what our assumptions are and how we're going to validate them is to break down the actual goals of the exploit into pieces. So you could do this exploit by looking at the source code and being like, okay, I see how big the stack is. I know basically the distance between here and here. I'm going to write some code and see if it works. And if it doesn't work, I'll write some different code and try that and see if it works. Or what you could do is break it down and say, I think the distance between my buffer and EBP is how many bytes? In this example, it's 100 hex bytes, and we know that from reading it. And so I'm going to write code that overwrites EBP first. And then I'm going to make sure that when I run that code, I overwrote EBP. That's step one, and I can save that off, right? And then I'm going to get control of EIP. And then I'm going to point EIP at something that I can control to make sure that I can run code. And then I'm going to replace that code with shell code. So I've broken that one problem up into these 5 pieces, and at each step I can validate myself, right? Now, if you don't do that, you run the risk of getting about halfway through the program and then screwing something up minor that's very subtle, like you wrote the pointer in with 1 byte off, or you tried to run the Python with backticks and the input didn't actually get into the program, so now it's crashing, but it's crashing in this crazy way that doesn't make any sense to you anymore. And if you haven't broken the problem down into those steps, you have to start over from the beginning, right? So you want to externalize your mental stack of what's going on in this exploit onto a piece of paper. Now you can use a text editor, a notepad, or you can use a notebook on your desk. I suggest you use a notepad on your desk, and you come up with a system for yourself. And in this system, you will probably need to note down a number of different things. You will probably want to draw your stack with all of your data structures. That'll be the first thing you do. The second thing you're probably going to want to do is break down the problem into those steps. Say, prove I can overwrite EVP. Prove I can overwrite EIP. Prove I can point at code that I can control somewhere. Okay, prove that it runs. Now get my shell, right? And at every step of the way, you're going to be setting breakpoints. And we'll talk about what breakpoints are in just a second. You want to write down the address of the breakpoint, why you set the breakpoint, and what it's meant to prove. Because if you're 3 steps into your problem and you have to restart your debugger and you lose all your breakpoints, you are going to be real lost, right? But if you wrote that stuff down and you were like, oh, breakpoint 3 is meant to do this. I've solved breakpoint 1 and 2. I don't need to set them next time I restart the thing, but I'm going to start 3, 4, and 5. Now I know what they're there for immediately. Does that all make sense to everybody? Right? This is very important to not drive yourself crazy. And so when we do the homeworks, I'm going to be asking you to show your work. And that's not because I'm a draconian math teacher. It's because I want you to get into the habit of not squeaking yourself over, right? And this is the way to do that. Okay, so has everybody drawn the stack and has everybody got this up in debugger? Does everybody know how to get to this screen so they can see it? Everybody's got that up on their monitor? If not, please let us know and we'll run around and help you. You look confused.
I'm
You want to whisper in my ear, or are you good?
No, I'm good.
Okay, cool. So, if you've all got this up and you've got your stack drawn, does somebody want to come up and draw their stack on the board? Be confident. Somebody beat you to it. And I always ask you questions. What's your name?
Alex.
Nice job, Alex. Thank you so much. While Alex is so kindly putting himself on the line here to show us what the stack looks like, please make sure that you've got access to that makeneg.py or whatever I called it. What is it? Yeah, makeneg.py. That's your template that you're going to use to write this exploit, okay? That's what your template's going to look like. A lot of people in previous classes have used Pwn Tools to do this work. This does everything that Pwn Tools does for you, and you're not going to have to use Pwn Tools to do it. You can just do it by hand, and you'll understand how it works. And then when you get to a problem Pwn Tools can't solve, you'll still be able to solve it. Okay? So that is why there are 2 imports here, one for sys and one for struct. And then there are 2 function calls in here that we are going to have to be using in all of our exploits. Okay? Let's see how this works. What's this?
It's RB at index 1. I don't know. The assembly gets the address at RB, and then it gets or adds 4 to it, and then gets the like where it points to again.
Okay, so there's one small modification I'm going to make to this. Cool. Okay, so you have this down here. Oh, and these are your arguments to stir copy. Yes, you're correct. Okay. Yeah. So those are pointers. Okay. Yes, that's right. Let me draw EBP up here too. Oh, it's here. There's EBP. There's ESP. Okay. So yes, this is what our stack looks like at the time that we call stir copy. Okay. Let us feast our eyes on this template, and we'll go through the template, and we're going to start piecewise, taking notes and working through this problem together so you can see exactly the breakdown.
Are the binaries posted anywhere?
Yeah, so on the canvas, there's ip.tgz. You don't have access. Are you in the Discord right now?
Yeah.
Binaries in the VM, aren't they?
I think
Please send me a text message on Discord and I'll drop it.
yes. The first argument is that way it's hard to be fun. So that's just where and then E references what? So what do you think is a large space for variables? Okay.
Okay, there you go.
Thank you. I have a question about that stack diagram. Are we missing the 256 bytes?
That's an argument.
So the mistake that he made here is these guys here should actually be down here. So you're missing, you couldn't see this line at the bottom, right?
Oh,
Yeah.
okay, yeah.
Let me redraw that a little bit, so to fix this problem. So that's it.
Can you possibly just rewrite the whole thing if you don't mind? Because I'm not gonna lie, that's kind of.
Yep, I can. Can you not see it over here? Shall I move it to the left for you?
Just a bit like too small. Like, I figured I could just do that.
Yep. Okay. So we've got.
No, green was just green has another thing. I didn't know what the thing. I didn't know that. Larry's idea. Put yourself down too.
Getting into my thing?
I want to be able to stop.
Oh.
I know, I'm not on this thing.
Yeah, I'm in yours.
I
just did these theories of the.
Killed it. I didn't know that you buy any. We're expecting. She wants to know whether.
Real MVM's password.
Or there's an outlier. There's an outlier. There's an outlier. You want another green one? I don't want to do it myself. I didn't know how I'm actually labeling myself. Okay, no, she's not. Okay, organization.
Cool.
Thank you.
These numbers, these pluses and minuses that I've drawn here are offsets from EBP. So when you look at in the source code, they'll be referenceable. Okay, so let's talk through that template real quick so you can understand what I've provided you there and why I provided it to you and what we need to change. You've been provided a couple things. The first is a struct.pack line. Struct.pack does what the P32 function in Pwn Tools does. What does that do? it allows you to say, take this number here, this integer, I'm providing you it as a long, and I want you to pack it as little endian, okay? So you could write a number as data by hand and have to do that process manually every time you change the number, or you can use the struct.pack function and just write the number there. And so if I put this there and I overrode a register with that, when I looked at the register, it would be correct. You would see AA, BB, CC, DD in the register, not backwards, like you would if you wrote the numbers out and you just put them in, okay? It also turns it into a binary string. That's the type in Python that it will output to you. And we are going to be, in our output, concatenating together a set of binary strings, okay? So whenever we make a string constant, we put that B in front of it, and that says, just freaking put what I told you to put there. Don't mess with it and try to turn it into ASCII, which is what it's going to do if you don't do that, right? We want to be like, no, I know what I'm doing, and that's what the B tells it. So each of these lines, these are your shell codes that I'm providing to you. This is the shell code that you will use in every homework. It is in this template, okay? So this template can be used for all of the homeworks you ever do in here. And you're going to use this shell code. This shell code will pop a shell. So you are going to, in the course of this example, replace the code that's running, ABO1, with your own code. This is the code that you are going to replace the program with, and it will run a shell. Why would we want to do this in the wild as a hacker?
You want to run a shell, we can access our own resources.
Yeah. You will now be the user that ran the program in the first place. In this example, you are running the program. You're not going to gain any access from that. But imagine if the program we are sending input to is a server, like a web server. And we have sent it this input, and we have replaced the web server with a shell that you have. Now you have the access that the web server had, okay? Our goal, whenever we write an exploit, a memory corruption exploit, is arbitrary execution of code, okay? We replace their program with our program, and we want it to be whatever we want, okay? Now, sometimes the easiest way to do that is with shellcode, and sometimes the easiest way to do that is simply returning to a function call that it normally wouldn't run there, that we would like it to run, okay? And we'll talk about that distinction in a second. This is the shellcode you're gonna run, and it will always pop a shell. You can then type ls or who am I or whatever, and it'll run like a normal shell, okay? This shellcode is a modification of this shellcode. This is for grading. This is the shellcode that Jay's program AutoGrader will run. And this one just prints out I win on the page, okay? The last line at the bottom here is for Python 3 specifically. This is our output, write sys.standardout.buffer.write, and it will allow us to write a binary string without it messing with it on us.
Sounds alright, like all those hex codes. What's it mean?
What do the hex codes mean?
Yeah.
Those are opcodes. Those are native code that the processor can read. And I will show you how to read exactly what that says in the debugger.
Does it read this and then translate it to the left, like to the assembly instructions?
Yeah, this is direct assembly opcodes. That's what the shellcode is. And so how did I build that? The way that I built that is using that gadgets.asm program, and I called an assembler, not a compiler, NASM, and the line you are going to use, because you'll have to do this yourself later, is NASM-F ELF32, and then your input. In this case, it's the ASM file. The other way to do that would be -F bin, and the difference between the two is if I put an ELF output, what it's going to provide me is a program that I can link into another program. So when I made gadgets, I did it with an ELF output, and I linked it in So if you are in your debugger right now, you can type just as gadgets and see what's in that file. If I did it with bin, it would not put any of the headers around it. All it would output directly is something that looks like this, right here. And if you were to use hex dump or obj dump to disassemble that, it would just show you those. And so what I did is, I wrote it, I compiled it with fbin, I hex dumped it, and then I copied and pasted it into there. And that's how I wrote that shellcode, okay? Just using the assembler and a hex editor. You will not be required to write shellcode in this class, because it is kind of fiddly. The reason it's kind of fiddly is that when you assemble something, you are going to get characters that strcpy cannot consume, right? Why does strcpy stop copying?
If it gets a null byte.
If it gets a null byte. So what happens if there's a null byte inside my shellcode? It's not going to work. You're going to get to the point in the shellcode, it's going to stop copying, your exploit's not going to work. There are a lot of characters that are prohibitive that you can't send in, and there are ways to get around that. We're not there yet, right? So I'm handing you this shellcode so you don't have to deal with that right now. All you need to know is this needs to be in memory. It's got to be at an executable page, and you got to point EIP. Once you do that, you win. And that's the goal of this thing. So what I would like you to do next is take this template, and you are going to modify this sys.standardout.buffer.writeLine to overwrite EBP, and you are going to overwrite it with just a string DCBA. Okay? So in the template up here, there's buff. Change that to DCBA, and you're going to change this line to put in enough characters to overwrite it. So you're going to write some number of A's, and then you're going to write those 4 bytes over EBP. Okay? So if you want to write some number of A's, the line you're going to write is the quote A times the number of A's you want to write. Now I have provided you a variable up here that you may change to figure that out and put in there. Yes?
I don't know if this was meant to happen, but I think the makeanegg.py file that you sent out, or at least the one that I have accessible on the virtual machine, I think already has the answer.
Already has what?
The answer.
Oh, does it?
We don't know. Not on campus.
Just what shellcode was it?
Let's see.
That's the answer.
Probably done.
Oh yeah, that's wrong.
All right.
You can use that example if you want, but it is wrong. So.
Yeah, sorry. I just wanted to clarify.
Yeah, no problem. Yeah, that's incorrect.
There's one in the homework too. I think it's also incorrect.
Yeah.
Yeah, the TA folder solution also doesn't work.
Yeah.
I guess that's a good thing.
Yeah, so they're examples, but they're not the ones I want you to use. But this is you're going to edit this line right now. There'll be a couple things that you need to edit to be very explicit here, okay? You're going to need to change this line to be this, then your EBP, right? And then you need to change these 2 values. Okay? And so does everybody understand basically what I'm asking you to do here to overwrite that EBP? You have one question that needs to be answered. And the answer is, the question is, how big does buffline need to be for you to fill up enough space to overwrite EBP on that stack? Okay? And if you have drawn your stack, you should have that answer sitting in front of you right now. Is that clear? Does everybody understand what I'm asking for there? Cool. So write yourself that script, and this is how you're going to test it. When does the overwrite take place in that program?
After the string copy.
After the string copy. The string copy is what does the overwrite, okay? So if you go here and you set a breakpoint, and then you look at EBP on the stack, you will be able to prove that it is what you expect it to be, okay? Now, how do we set breakpoints? How do we look at the memory? How do we prove it? There are two things that you need to understand in order to do that. First is, three things. The first is how to run the program, right? And so when we run the program, we are going to use the command, man, I wish I had more whiteboards, please. We're going to use the command R, big shocker there, and then to put your output in, that Python script is outputting to standard out, right? Your program is reading an argument. So how do I get standard out from one program as an argument to another program? I use backticks. This is the way that I do it. There are other ways to do it. Anything within backticks, what that means is to the shell, run the program, take the output, use that as a string. Okay? So in this case, because the Python script already has the shebang at the top, /user bin Python, you don't have to say Python 3. You could say Python 3 space script name, but you could also just say // make an egg .py. And that'll write it out. Okay? So that will get it in there. That's going to run all the way through and then crash. That's what will happen if you run it like this. So how do you stop it and validate yourself? Well, use breakpoints. Breakpoints, BR adder. Okay? The syntax for it is you will provide this address here as an argument, and before this instruction is run, if you break on this number, it's going to stop the program immediately before running this move. It'll stop it right here. If I did 8.4, it'll stop it right here, okay? How does it do that? The way that it does it is it has a table of replacement code. So these are software breakpoints. Hardware breakpoints work a little bit differently, and they are limited. Software breakpoints are theoretically, you have an unlimited number. There is an instruction, 0xcc. That is the trap instruction. Debug trap. When the kernel sees that that instruction has been executed, it throws that sig trap signal, and it gets captured by the debugger, and the debugger stops there. Okay? And when we set a breakpoint, that debugger overwrites the opcode, one of these guys, with the number CC. Okay? And when it gets there, it replaces it back again by looking at its table that it saved off. This has a couple implications. The first is, if we set a breakpoint on a code page, we're all good. Code pages don't change. However, if you were to set a breakpoint on the stack and then write your data over the stack, you would overwrite the breakpoint. The debugger would still tell you that a breakpoint is there because it's in its table, but it's not going to work. So if you want to set a breakpoint on shellcode that lives in changeable memory, you have to make sure you set the breakpoint after that memory got changed. Okay? Another way you can do this is hard code the trap in. So what you are going to do, if you want to break before your shellcode runs, and you do want to do this, I promise you, you're going to go over to your shellcode and you're going to make a small modification. You are going to put right here /xcc. You'll just add one character to the start of that shellcode. And now, when you run the shellcode, instead of running straight through and giving you the shell, it will set a breakpoint. And that will allow you to validate yourself yet again. Okay, so that's going to be one of your other validation points. So,
one small thing with breakpoints. You should probably add a star before the address, otherwise it will not set properly.
yes.
Syntax of it.
In GDB, Yeah, sorry. We don't want to break on the number, we want to break on the memory that's at that address. So you always put a star in front of your address or a star in front of your symbol. So you could say break main plus 30. That would work too. So let's write our program to overwrite EBP. And does anybody have that done already? How big is bufflen going to be in this example?
Hex 100.
Hex 100. How did you figure that out?
Like when we subtracted down 100 and right there.
There are several ways we can figure this out, actually. If you drew your stack correctly, you can very easily see the argument that we sent. We got that pointer from the load effective address line, right? That's where we get the pointer to our destination. Well, it's EBP minus 100. And EBP, the register, is pointing at the old EBP on the stack. The space here, between here and here, is 100 hex bytes. Okay? So if you set bufflen to 100, set bufflen to 100, that's the first answer to this. And EBP is going to be set to DCBA, and we can validate that. Okay? That'll get you that overwrite of EBP. If you wanted to prove that, you could then set the breakpoint and go look at the data on the stack. Now, if we wanted to print out our stack, we would have to use the debugger's functionality to examine memory. And the function that lets us examine memory is X for examine. Now, it lets us format that memory in a way that makes sense, because otherwise, assembly has no concept of types. There's no way for us to know what it's going to spit back out, or for it to know how you want to see it. And so you can give it formatting. So the formats that we have access to define how to show us the memory, and then how big we want that data chunk to be. And so if I said X slash 4X, that would show me 4 D words. It would show me 4 4-byte chunks as hex. So I'm doing that real quick. Okay, so that's me setting the breakpoint at main plus 30, so immediately after the call. And then we are going to input our program, and I'm just going to write it by hand here. So 3-C. Actually, I'll write the script. I'm not going to do it by hand. So CBA 100 hex. You're going to write A times bufflen plus EBP okay. So I've sent it this input here. That A times bufflen plus my EBP. Bufflen's 100, EBP's DCBA. And I set the break immediately after the syscall. Now let's do this. X slash this is going to give me 100 D words starting at ESP. So now I'm running this on my machine, not on the VM. There's somebody running on the VM who does this for me is going to have to take a look and see exactly what the stack address is on here. So on my machine, I'm starting at FFFF. That's like the beginning of the page, right? So when I dump this out, it's not going to be in the order that you expect it to be in. It's actually backwards because it's starting low and going high downward, which is not how we draw our stack. But what you can see from dumping this out is that we've got 2 stack pointers, right? Yours are probably going to be BFFF. They should be. Those 2 stack pointers we see here are these 2 pointers right here. Then I've got a whole bunch of A's. 4-1 is my ASCII for the A's, right? So I can see those A's in memory. And then I start to see more stack addresses. Okay, so here's the end of my buffer. Here is 41, 42, 43, 44. That there is the DCBA that I just printed out. I overwrote EBP with. Okay, and we can so now we're here. Then the next thing we should see is a code page address, and we do. And then the next thing we should see is argc. So that's our and then there's argc, and argc in this case is 2, because the first argument was the name of the program, and the second was what we put in. There's our argc. And then here is another stack pointer, argv. Okay, now how do I know that's argv? How would I prove that? My assumption is that's argv. It looks right to me. What if I were Curious George and I really wanted to prove that? I could look at that memory. I could say x slash, what I'm going to expect to see, here's my assumption. My assumption is that that's the argv array. So it should be 2 more pointers and then a null, right? So let's print out 3 hex of that number, and let's see if I get 2 stack addresses and a null. 2 stack addresses and a null. Okay? If I were to print one of these stack addresses out as a string, what would I expect to see?
Program name.
I would expect to see the program name. I'll do that. Examine/s to print it out as a string. That means cast this to a string and show it to me. What do I expect to see when I hit enter? ABO1. Okay? If I do it again here, what do I expect to see?
X100As.
X100As, DCBA, that's it, right? A repeats 200 times, okay? So that's a quick magic trick that you can do if you understand how to use your debugger. Did everybody follow that extremely quick thing that I'm tearing through because I wish I had 4 hours to do this lab, but I only have an hour and 15 minutes?
Got the cheat sheet.
Right? Is anybody like completely lost right now? Please let me know if you are. Are you? A little bit? All right, so we're gonna do office hours after this that last like 4 hours, and I'm gonna sit down with each of you individually and like walk you through this again. But what I did there is set my assumptions, use the debugger to validate my assumptions, step by step, right? Okay, so let's make one more change to the script now that we've proven that we've got EBP. I'm not going to ask you to make that EBP proof normally, okay? What I'm going to ask you to do is to hit ret dead on. And you don't have to set any breakpoints to do that because the program will crash if you do that, okay? So we're going to go up here to ret, and we're going to add this to the end of the line. Ret. Okay? And so now, our first program overrode up to here. We added another 4 bytes to the end. Now we're going to overwrite to here. Okay? I'm going to run this program with no breakpoints. What's going to happen?
Crash.
Why is it going to crash?
It's going to return the AABB.
Yes. We are going to overwrite the return pointer on the stack. That program will then finish running without crashing. And it will roll up the stack. It will go leave, and it'll pop EVP off the stack, and then it'll go red, and it'll pop red off the stack. And we will have overwritten that with AABBCCDD. Okay? And so when we return, that will segfault. Why will it segfault? What does it mean to segfault?
You're going to an invalid memory location?
I'm going to an invalid memory location. I am asking the processor to read memory from an address that does not have a segment attached to it. So when it goes through that page table and does its hierarchical lookup, it'll be like, I don't have any pages that are mapped to AABB. And so I am going to throw an error that is a seg fault. That is what a segmentation fault is. It means you read from or wrote to memory that does not have a physical page backing it. Okay? So anytime you see a seg fault in your program, it means you wrote to a pointer or you read from a pointer that is bogus. You corrupted that pointer somehow, or your data structure was not valid. Okay? So let's go back and we'll clear our big points. You have got that GDB cheat sheet, which shows you how all of these things work. And it will be on you to use that cheat sheet and get comfortable with messing with this and doing what I am doing right now. Okay? That's kind of the point of this easy example, is to get you into the debugger and be messing with it. So let's clear everything. I'll get like a totally clean, yes. GDB. Do people have classes immediately after this?
Yes.
God damn it. All right, we got 15 minutes. We can still do it. All right, so we're going to run this program with bufflen, EVP, and rep. Right? So how am I going to do that? Just with those backticks one more time. And when I run this, we should see that seg fault. And then how are we going to figure out what happened? Here's our seg fault. Program received signal, sig-seg-v segmentation fault. AA, BB, CC, DD in question mark. I don't have a page map for that. I don't know where it is. Okay? So how do we know what register stored that value that the bad read was from? Well, there's two things we can do now. We can say, what instruction just ran? We don't know because EIP, which is what I just referenced there, is pointing at AABB, CCDD. Okay, well, what if I do? Show me all of the values of the registers. Info, reg. We can see two interesting things here. We can see EIP is AABB, okay? That instruction pointer that determines what instruction runs next, we control it. If you are a white hat, class is over, you can go home right now. You get an A, you're done. Get your CVE, get the program fixed. Second thing we can see here is EVP. We overwrote that with 41, 42, 43, 44. Okay? The reason I had you do DCBA and not ABCD is so that you would have a visual representation of little endian byte swapping going on. In order to get 41, 42, 43, 44, which is ABCD, we had to give it DCBA. Right? Struct.pack handles that for us. We asked it AABBCCDD. It gave it to us in that order. That's why struct.pack is there for us. Right? You could write your numbers manually and manually flip them and manually convert them into /x whatever, just like we're doing with the shellcode. But struct.pack makes it easier. Note the structure of the script that you've got. Everything is broken out into named variables. You could write this exploit as a string of text. It would work. but you would never be able to figure out how to fix it. And if you had to give that homework to one of your friends to cheat off of, they would have to know exactly what you'd done in order for it to be useful to them at all, right? If you break it out into variables and you comment them, one, you make it easy to make changes to the exploit. Two, you make the exploit make sense. 3, in 6 months when you have to go fix it because a new version of the program came out and all of the offsets are different, you'll remember what you did 6 months ago and you'll be able to fix it easily. The final project that I would like people to do, this is not going to be required, but what I would like people to do is to go out and find an exploit somebody had already written in a real program and then do the write-up. So rewrite the exploit, break it out into the variables, comment the variables, and write a document. And that document is as much information as you would need to rewrite this in a year without having looked at it in between. That's what the goal would be for that final project. That would be a really good final project. Okay? So we have now written a script that takes control of EIP. We have a couple options if we're black hats and we want to finish this job. So the first is the simplest, and that is the example that was written there. And what that does is it puts the shell code, which is the code we're going to execute. Looking for a pen, here it is. It puts it right here. Okay. And then it points the return address statically into our stack. This makes a big assumption. In this case, we will always be executing our shellcode on the stack. The stack is executable page. That's fine. The problem is if you make an assumption about where the stack is. On different computers, the stack will move around, right? On your VM and someone else's VM, or somebody else's Linux machine, or somebody else's VM on the CSRF servers that you probably get later, that stack will be different. The reason the stack will be different is because of all the stuff that happens before is different. The environment variables on the computer are different. The actual hardware will make a difference. How many other people have used the computer today before you will make a difference. And so we can't rely upon that. If you write the exploit and it works on your computer and you pass it in and you say, works for me, that's not good enough. And that is why we don't return the stack addresses. If you are a white hat, you can do that because your goal is to prove it's exploitable. And if it works for me, that's good enough. If you actually have to use it for something, it has to work everywhere, or you're going to burn your bug. It will crash. There will be a crash dump that will get sent to Microsoft, and theoretically, in the next 20 years, someone will look at it, right? If 500 people have sent it in, or you've sent this out to a lot of things, there's a lot of crash dumps, the odds of them looking at it go up exponentially, right? If you are running your web browser, and the web browser hangs, and then your computer starts running like crap, you may become suspicious. You may be like, who's mining Bitcoin on my computer right now, right? So we do not like it when people's program crashes on our exploit. We want that sucker to run and run perfectly. So how do we return to something that's always reliable? This is what that gadgets is for. Normally, when you are writing ROP code, there are two challenges for ROP. And what ROP is return-oriented programming. Once you have access to EIP, once you control EIP, the question is, where do I point it, right? And what ROP says is, oh, I point it at existing code in code pages that doesn't move, okay? And you can chain those pieces of existing code together. In this example, I'm going to give you a single piece of code that solves the whole problem. And you will always be allowed to use that, okay? So in one of your homework examples, you may have to modify gadgets and recompile the program. Now this seems like cheating, but what I am doing here is giving you an out. If I asked you to find your gadgets in libc It may take you many, many months to do that without some tooling that you've made. So I'm just gonna let you take it as written that these gadgets exist. Okay, and that's what gadgets.asm provides you. So everybody do this now in your debugger. You should be able to say with this binary that you have this ass space underscore is important, gadgets, and you should see this code pop up. This is code I have linked in here specifically to solve this problem. Okay? Where we are going to point return is this address right here. Why are we going to do that? When we do that, this instruction will be executed next, and that will be jump ESP. Now, ESP, at the time of our crash, is important. Where does ESP point on this stack at the time of our crash? Some brave soul, come down here, take this pen, and write an arrow. Quickly, we have 5 minutes. Who's brave? I'm gonna call on someone. Stefan, hobble your ass over here. No. You're the one with the not working leg. You know what I'm doing.
You want me to do it? I'll come up.
Yeah, okay, yeah, sure. If you know where it goes. Guys, look what you have done. This is on all of your cowardice. I never want to see this happen again.
Pretty sure it points at the return address.
We just popped return.
Then right here.
Correct. How did you know that?
Because we just popped return.
We just popped return off the stack, right? If that return value is in EIP, we popped it off the stack. Ret does two things, right? What are the two instructions that ret performs? Yeah, what's ret do? It pops the next thing off the stack into EIP. Right? That's what it does. And so then now you've incremented the stack by 4 bytes, and you are now executing the instruction that was pointed to by that pointer on the stack. Right? So ESP is right here. Just above ret. Okay? We don't necessarily need these two things to be intact for our program to run. We're done using, when we pop out of main, we're done using main. This whole stack frame now is basically useless. It is below ESP. Everything under ESP is garbage, right? These two guys right here are immediately going to be popped off the stack as well to clean up the arguments to main. They won't be used again. So we can kind of make an assumption, which we will, which is that this data is not necessary. And so we're going to make a small modification to our script to add the shellcode in. And it's going to be like this. We want it to be immediately after ret on the stack. That's where ESP is pointing. So we're going to put our shellcode right there. Okay? To validate our assumptions, I'm going to add that trap there. So that the first thing that happens if we happen to execute our shellcode, which we will, is that that trap will set off. And now we can look at what's going on in our debugger. Okay? The next thing we're going to do is actually set ret to point at the shellcode. And we're going to do it by way of jump ESP. What you could do is put the stack address in there. You could say, at the time of crash, where's my stack? Oh, it's BFFF something, something, something. Point it there and jump back into the stack. That would be sloppy because the stack moves around and it probably won't work all the time. It won't even work 2 times in a row, but it'll work once, right? What we're going to put in instead is this number that I've highlighted, 08049190. And that will jump us to jump ESP. 08049190. Okay? And I'm going to validate myself again, and this is how I'm going to do it. Let's clear everything. So So I'm going to set a breakpoint on that value, 0x08049190. Now there are two breakpoints on this program. The first breakpoint is the one I just set on jump ESP. The other one is right at the start of the shellcode. I put that in manually by adding /xcc. So there are two break instructions in our program flow now. Okay? So we're going to have two breaks to look through. The first time I run this, and once again, this is the final